Now let's go through a bunch of examples kind of quickly because we've done this already. I have a matrix here, all prime numbers, 3 by 3 matrix. What's its rank? It is 3. What is its column space? It's all of R3. Does X equal to B have solutions? How many solutions? It's unique because this is invertible. So the solution is just the inverse of this matrix times whatever B you have, and that will always give you just one solution. What's its row space? It's again R3. What's a good basis for the row space and the column space? The identity matrix. So remember, all invertible matrices will have the same row space and column space. So invertible will imply that it is a square matrix. It will also imply that it's full rank. That means they will have all of the input space and the output space, which are the same spaces, and they will all row reduce to the identity matrix by Gauss-Jordan. And the fancy way of saying that is that they are row and column equivalent to each other. Row equivalent means you can get from one to the other using elementary row operations, and column equivalent means you can do the same using elementary column operations. So let's go from the example to a generalization. A full rank square matrix will row reduce to an identity matrix, and that would be a good basis for the column space and row space. So the column space is Rn, row space is Rn, null space is not empty but set with just the zero vector. This is actually troublesome philosophically because I don't know whether to call this empty or not, but I prefer not empty. So if I have a question in a quiz or the final exam asking you, is the null space empty? Do not say it is empty. In my book, it is not empty because it's got a zero vector in it. Alright, if it is rank deficient, then the row reduction will give you n minus r rows in 0 rows in the bottom and some free variables, n minus r of them, and that will be mingled in with an identity matrix. So the column space will be a subset of Rn with dimension same as rank. The row space also a subset of Rn, same dimension. The nullity is a dimension of the null space, n minus r. The left nullity, the dimension of the left null space, is also n minus r. Now let's take another example, a full column rank matrix. So it's the same as the previous guy that I added one more row here. And if you do the RREF, you will get the identity matrix in the top and zero row in the bottom. What's the rank of this guy? 3, because 3 linearly independent columns. What is the column space of this guy? Remember, when I'm asking for column space, I'm asking for the containing space, dimension, and the basis vectors. The containing spaces are 4, yes, but what about the dimension? Dimension 3. And the basis vectors will be the 3 columns of A, not of RREF. 3 columns. Does AX equal to B have solutions? Now it becomes a bit more complicated. Does it have solutions? Depends on consistency because you have a 0 row. So it is possible that this can be equal to some number B, not 0, in which case it won't have solution. But what if it happens to be 0, then how many solutions will it have? Unique. So either unique or no solution. So that's the situation here. What's the row space of this guy? It's R3. Is it all of R3 or a subspace in R3? Is a subspace of R3 with dimension 3, which means it's all of R3. Okay, it's all of R3. So all full column rank matrices will row reduce to something like an identity matrix on top with some 0 rows in the bottom. It may have solutions if B is in the column space of the matrix, which means the last one will be equal to 0. It is not then 0 solution. If B is in the column space, then 1 solution, unique solution. Never an infinity of solutions. The row space is all of R3. So all full column rank matrices will row reduce to that. Okay. Now the same thing again using symbols rather than numbers. So we saw all those things, but let me just say that the column space is got m. Each column has got m elements, so it's in Rm. Dimension is n because it's full column rank. The rank is the number of columns, which is n, and the row space is all of Rn. Null space it's got only the 0 vector in it. The left null space, on the other hand, it's got m minus n vectors in it. If it is rank deficient, similar kind of situation, except that I don't have dimension n but dimension r, which is the rank of the matrix. So similar kind of story. Couple of more examples. Full row rank. So I have 3 rows here and 4 columns here, and my RREF is going to be that. So what's the rank of this matrix? It's again 3 because 3 rows, and those are linearly independent, but you can see the pivots right here. That is 3 also. That is a rank. What's its a column space? All of R3. Each vector is in R3, and I already have the full basis here and then something extra. So it is all of R3. Does Ax equal to B have solutions? Is there a possibility that this matrix might lead to inconsistent equations? No, because there is no zero row, so you cannot have inconsistency. And there is a free variable here corresponding to this column, pivotless column. So infinity of solutions. Always infinity, never unique. The row space will be, what's the row space? It's going to be a subset of R4 with dimension equal to the rank, which is 3. The rank is 3. The row reduction, as you can see, is identity matrix, possibly mixed in with free variables. It doesn't necessarily have to be cleanly separated. Always, so once more, so the row space, the column space, if it is a wide and full rank, the column space is all of Rm. M is the output space, and the row space will have the same dimension m, but it's because n is larger than n, it's a subset. And the null space will have nullity, which is n minus m. M is a rank. If it is rank deficient, then the situation is same as before. The dimension of column space and row space will be the rank. Nullity will be the number of columns minus the rank, and the left nullity, number of rows minus the rank. So a general case, I will just write that once more. Dimension of row space is R, dimension of column space is R, and nullity is n minus R, number of columns, number of variables minus R, the number of free variables. Nullity is the number of free variables, and the left nullity is the number of rows without pivots, that is m minus R. Now computing the 4 spaces, that is an important topic. If I have a 3 by 4 matrix, what I would do to compute the column space would be to do the row reduction, Gaussian elimination, so that I can find the pivots. I get the pivots, then I go back to the original matrix and take the pivot columns, the first one and the third one. That will give me the basis columns, and number of pivots will give me the dimension, and the number of elements here will give me the containing space. So column space will live in because each column has 3 elements. So it's a subset of R3, and the rank will be the number of pivots. So I have 2 here, so the rank is 2. That will be the dimension of the column space. So this will be the kind of answer I'll give. Column space is a subset of R3, dimension is 2. Then I'll specify the basis, which will be the first one and the third one, 1, 2, 1 and 1, 1, 0. That will be the basis. The pivot columns in the original matrix. The row space, the same idea. I would do the row reduction, maybe REF, maybe RREF, it doesn't really matter. I will see the pivots here and here. So 2 pivots, and my row space will have 4 components in each vector. So that lives in R4, that's the containing space. And there are 2 linearly independent rows because those are the pivot rows, either in the original matrix or in its row reduced forms. It doesn't matter. So let me take it in from the RREF this time. So the first row is 1, 1, 0, 3. But when I give a basis, I would like to see column vectors. So that is the 1, 1, 0, 3. That will be a basis vector. The other one will be 0, 0, 1, 3. 0, 0, 1, 3. So 2 basis vectors, dimension 2 is the same as the rank, living in R4. Computing the null space is much more interesting. I'll give you one example here. Now I'm going to call, I started from a matrix A. I did row reduction, Gaussian elimination. Finally I got RREF. I'm going to call that R. Now if I have Ax equal to 0, that is the equation I have for null space, or R equal to 0, are the solutions going to be the same? In going from A to RREF, all I did were elementary row operations. They were like equation manipulation, algebraic manipulations of equations without changing the solution. So Ax equal to 0 and Rx equal to 0 will have the same solution set. So the null space of A and null space of R will be the same. So it's probably easier to work with this. So let's start working with that. First of all, null space also lives in R4 because it's a solution with 4 columns, 4 unknowns. So it's a vector of size 4. Rank will be the number of, rank of A is number of pivots. The dimension of the null space will be the nullity, which is 4 minus 2, which will be the number of free variables. So I have pivot here, so those variables I can solve, but this is a free variable because there's no pivot there. This is a free variable, no pivot there. So I have to find the solutions, the free variable, the complete solution. So I'll solve Rx equal to 0. So let me actually go ahead and solve this. So I have R equal to that, Rx equal to 0. This is free, x2 is free, x4 is free because no pivot. So I just look at the second row. The third row doesn't give me anything, so look at the second row. That reads 0x1, 0x2, 1x3 plus 3x4 is equal to 0. x3 plus 3x4 equal to 0. That implies, if I just solve for x3, I get 3x4. Remember, x4 is free variable, so I'm keeping x4 as a take any value for x4. So I solve for the non-free variables in terms of the free variables. If I take the first row, I have x1 plus x2 plus 3x4 equal to 0. So x1 in terms of the free variables is minus x2 minus 3x4. So I can write the solution. I have x1 right here, and I have x2 as x2 because that's a free variable, and x3 right here, and x4 as x4. And that I can decompose into the free variables, which can take any value, as a linear combination of two vectors here. Maybe I can call it t1, t2 because they can take any value. Okay, so it's linear combination of a couple of vectors, and those vectors are actually the basis for the null space, because any such linear combination when multiplied by a will give me the 0 value. So all the linear combinations will belong to null space. Now I can actually specify the null space. Null space is a subspace of R4 because 4 variables. Dimension is 2 because number of free variables. And the basis would be the complete solution that I just found here. Minus 1, 1, 0, 0, minus 3, 0, minus 3, 1. So it's a bit more tedious and more involved to find the null space. And you have to review this process of finding the complete solution. That's very important. And that is actually the process of finding the null space also. So I promised you